So now we are going to discussing about machine instructions and programs, and these are our objectives: machine instruction and program execution, including branching and subroutine call and return operations, and number representation and addition and subtraction in the 2's complement system, and addressing methods for accessing registers and memory operands, and assembly language for representing machine instructions, data and programs, and program control input and output operations. So these are our objectives. And now first we discuss about number, arithmetic operations and characters. And first we discuss about what is a number representation. And to represent number, we have three representations are there. So especially in this case we talking about signed integers. So what is the meaning of signed? Means whenever we can treat as a sign, here we have positive numbers and negative numbers. So to represent positive and negative numbers, we have three representations are there. The first one is sign magnitude representation. Second one is ones complement representation, and two's complement representation. So now first the representation of positive and negative numbers is sign and magnitude representation. So how we can represent sign and magnitude means always the MSB bit is considered as sign and remaining bits are considered as magnitude. So for positive numbers MSB bit is 0, for negative numbers MSB bit is 1. So by using here we have modulo n number system. So here we have one graphical representation of sign magnitude representation for positive numbers and negative numbers. Here n is equals to 16 means here we have 16 combinations are there. So in that 16 combinations are represented in inner circle, and outer we have plus 0, plus 1 to so plus 0 to plus 7 numbers are there. So by observing these plus 0 to plus 7, these are all positive numbers, so that the MSB bit is 0, and remaining 8 are minus 0 to minus 7. So observe these minus 0 to minus 7, the MSB bit is always for negative numbers 1, and remaining magnitude bits are same for positive numbers and negative numbers. So this is the representation of positive and negative numbers for sign magnitude representation by using modulo n number system. So for example 0, 1, 0, 0 is equals to plus 4. So for plus 4, because it is positive number, so that message MSB bit is 0. For minus 4, so it is negative, so that MSB bit is 1, and remaining magnitude bits are same for positive and negative numbers. So this is the representation of sign magnitude by using our modulo n representation. And now we discuss about the second representation of our numbers is signed ones complement representation. And signed ones complement is represented by using modulo systems, and here n is equals to 16. So n is nothing but number of combinations are possible, and these representations are represented in inner circle, and the outer we have the positive numbers and negative numbers, and plus 0 to plus 7 is positive number, and minus 7 to minus 0 is negative number. In this case also we have two representations for 0, one is positive and another one is negative. For observe here plus 0 and plus 7, it is same as in sign magnitude representation. So one important thing is for positive numbers in sign magnitude and also in sign ones complement we have same representation. But coming to the negative number, how we can get binary representation for negative number means by complementing the positive numbers. Here we represent signed 2's complement representation by using modulo n systems. Here n is equals to 16. So here we have 16 representations are there. So these are represented in inner circle, and here also we have positive numbers from plus 7, plus 0 to plus 7. So observe here sign magnitude, sign ones complement and sign two's complement for positive numbers is same, for only here we have the difference for negative numbers. In this case, how we can represent the negative number in sign two's complement means by taking the complement of positive number and add 1 to the complementing number. So we can get our 2's complement of negative number. So it is same as our 1's complement, only one one bit is shifted in clockwise direction, and here we have only one representation for 0 and one more negative number than our positive number. Here minus 8 is extra compared to our signed 1's complement and signed 2's complement. So it is very important representation because uh, in addition and subtraction we use signed 2's complement representation. So why we use only signed 2's complement representation means, so in whenever we use signed 1's complement for addition operation, whenever the carry is getting in our addition operation, so those are carry again added to our result. So we require another additional circuitry. But whenever we use signed 2's complement, the carry, whenever we are going to perform addition operation, there is any carry, that carry is discarded. So this is an efficient process to perform addition and subtraction. So we use signed 2's complement representation for addition and subtraction. So finally these are the three representations to representing the positive and negative numbers. So what is the final conclusion is, so for positive numbers, sign magnitude, sign 1's complement and sign 2's complement is same in all representation. For negative numbers only we have differ. So this is about our some representations of our sign magnitude, 1's complement and 2's complement. So these are the binary representations. So here plus 7 plus 7 plus 7. So for positive numbers all the representations are having same binary value, and for coming to the minus 0 and minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7 in our sign magnitude we have different. So like that we have, this is a table to indicating that how we are representing our sign magnitude, sign 1's complement and sign 2's complement. And now we discuss about addition and subtraction by using 2's complement. So while we are going to perform addition operation for signed numbers, so we have four combinations are there for signed numbers, and consider both are positive numbers and both are negative number, and one is positive and negative and another one is negative and positive. So these are the four combinations are there. So in these combinations, whenever we are considering the first case, that is both are positive. In our example the first case is both are positive, means 4 and 3. So we are going to perform addition operation. So we have positive numbers are having same representation. There is no bothering about how we can representing positive number. So for binary representation of 4 is 0 1 0 0, and the binary representation of plus 3 is 0 0 1 1. So we can perform addition operation. So there is no problem whenever we are going to perform positive numbers. Whenever we can consider any negative number in our two numbers, suppose here the second example we have two negative numbers are there. So here how we can write the binary expression for binary number for minus 4. So in the minus 4 we have three representation, but here only we can write the sign 2's complement of minus 4. Why? Because when performing addition and subtraction operation we consider only for negative number signed 2's complement representation. So here minus 4 and minus 3 is in 2's complement, and after that we can perform addition operation. Here we can get the carry, so that carry is discarded. So in this case the answer is in 2's complement form. So in the third case, here we have only one negative number is there. So 4 is as usually write 0 1 0 0, but for negative we write the 2's complement and perform addition operation, and here also we can discard the carry. So this is the way how we can perform addition operation whenever we have negative numbers. So one thing you have to remember, so for any combinations are there, suppose in a given number there is any negative number is there, so we can represent, while before going to perform addition operation we can represent our negative number in signed 2's complement, and after that we can perform addition operation. Whenever there is any carry we can discard. So that is the mechanism to perform addition operation by using signed 2's complement. But here while we are performing addition operation there is any overflow is occurred. So how we can detect our overflow for unsigned numbers? Whenever we can get carry out, so it is called as it is a overflow. But in this case it is not exactly whenever we can get carry out it is a overflow, but here we have some approach how we can detect the overflow. Means here we have the two carries are there, that is carry in and carry out. So which one is called as carry in means which the carry present in MSB position is called as carry in, and the carry present in outside the MSB bit is called as carry out. So whenever the both carries are not equal, we can say that overflow is occurs. And now we discuss about some examples how we can perform addition and subtraction by using 2's complement. Here we have number of examples and how we can perform addition and also subtraction. In the previous case in the previous slides we discussed how we can perform addition operation, and now we discuss about how we can perform subtraction by using 2's complement. So the first step is to observe here E, and here we having two negative numbers, that is minus 3 and minus 7. We have two negative numbers are there. So whenever we have any negative number in a given number, take 2's complement. So we can write the minus 3 and minus 7 in 2's complement, and after that take subtrahend 2's complement, means this subtraction is going to be converted into addition by taking the subtrahend 2's complement and add to the minute. So here subtrahend is considered as minus 7. So we can consider as we can take the 2's complement of minus 7 is we can get 0 1 1 1. So after that we are going to perform addition operation. So whenever one thing you have to remember that to represent negative number we use sign 2's complement, and we can perform subtraction operation we can use 2's complement. So this is a these are the different examples how we can perform addition and subtraction by using 2's complement. So this is how we can perform addition operation by using sign 2's complement, and also how we can get overflow whenever we are going to add positive numbers and negative numbers. And whenever we perform addition between positive numbers we can get negative number in the first case, that is 5 plus 3, here we can get minus 8. But whenever we are going to perform negative numbers, that is minus 7 and minus 2, we can get the plus 7. So whenever we are going to perform addition operation between same signs, we are getting our overflow. And now we discuss about some overflow condition while performing addition operation. So in the first example, consider when numbers 5 and 3. So here observe that 0 1 0 1 is our representation of 5 and 0 0 1 1 is our representation of 3. So there is no negative number, so we can normal binary representation here we can represent. And then we are going to perform addition operation. After addition operation, so here the carry in. So which one is called as carry in? The carry present in MSB bit is 1, and the carry out. So there is no carry out, so it is considered as 0. So whenever carry in and carry out are not equal, we can say the overflow is occurred. So in the first example we can get the overflow. Why? Because here carry in and carry out are not equal. And coming to the suppose the final example, that is minus 3 and minus 5. Here we have both negative numbers, so we can write the both negative numbers in sign 2's complement, and after that we can perform addition operation. And here we have the carry in and carry out. MSB bit, in the MSB bit position we have the carry is 1, and in the outside the MSB bit we have the carry is 1. So in this case we have the carry in and carry out are equal, so there is no overflow. So finally how we can find out the overflow is occurred or not in addition operation means by verifying the carry in and carry out. So whenever the carry in and carry out are not equal, so we can say that overflow is occurred. Now we discuss about instruction and instruction sequencing. So first of all, what is the instruction? Instruction is a one command to the computer to perform specified task, and every instruction must have the these operations and data transfer between the memory and processor registers, and it is capable of performing arithmetic and logical operations and data, and program sequencing and control, and input and output transfers. And here we have some representations and some notations are there how we can represent our instructions. And the first one is register transfer notation. So identify a location by symbolic name standing for its hardware binary address. So we have some addresses is there, so that address is represented by some symbolic name. So for example, location LOC is our symbolic name, and R0 is our representation of register, general purpose register. and the contents of location are denoted by placing the square brackets around the name of the location. So for example, so LOC in the braces we can represent. So means the what is the meaning of this one is R1, the location arrow marks indicating to R1. Here the information present in location is transferred to register. And the next one is suppose R1 and R2 are added and these are stored in R3. Means the R1 contents R2 contents are added and the result is stored in R3. So this is nothing but register transfer notation. And another notation is assembly language notation, represent machine instructions and programs. And here we use some mnemonics like move, add. So these are the some mnemonics, and these are the mnemonics used in our assembly language programs. And here it is same. In the previous case we can discuss the location, the information present in location is transferred to R1. Here we indicating that arrow mark, but here irrespective of that, here we use some instruction. So assembly language notation, that is move LOC comma R0. So always the instruction, the first operand is source operand and the second operand is destination operand. What is the source operand here? LOC is the source operand and R1 is the destination operand. So what is the meaning of move location comma R0? R1 is the contents present in location is transferred to register. And the second one is add R1, R2, R3. Irrespective of using the register transfer notation, here in the right side we can represent R1, R2 is stored in our R3. Irrespective of that, by using assembly language notation we use add R1, R2 and R3. So what is the meaning of here? Means the contents of R1, R2, R3 are added and the result is stored in R3. So this is the representation of assembly language notation. And here we have different instructions are there. So here we have three different types of instruction formats are there. So the first one is 3 address instruction and 2 address instruction, 1 address instruction and 0 address instruction, and also we have some risk instructions are there. So what are the 3 address instructions? Means here in the instruction we have 3 operands are there, that is called 3 address instruction. Means 2 source operand and 1 destination operand. So here for example 3 address instruction is add R1, R2, R3. Here we have the R1 and R2 are the source operands and the R3 is the destination operand. And coming to the 2 address instruction, add R1, R2. So here we have 2 operands are there. So in that 2 operands, one is considered as source operand. The first one is considered as source operand and second one is considered as destination operand. In some computers, the first we can represent destination operand and then we discussed and we can represent source operand. So now we can discuss only the first operand is source operand and the second one is destination operand. And coming to the 1 address instruction. 1 address instruction. So here we have only 1 operand. So here we can for example the 1 address instruction means add M. So means whenever it is there is no register, it is automatically stored into or automatically perform addition operation. So here add M means only we have 1 operand. And 0 address instruction add. So there is no operand present in our instruction. So these are the different instruction formats present in our programs. And now we discuss about the different instruction formats one by one. And here I am considering one example how we can perform A plus B into C plus D. By using 3 address instruction, how we can perform this instruction execution. First of all, we have performed addition operation between A and B and storing this addition into R1 register. And so because of that, here we have 2 source operands and 1 destination operand. And the second instruction, and add C comma D, and these are stored into R2. So here also we have C and D are the source operand and R2 is the destination operand. And mul. So after addition operation, and here we are going to perform multiplication between A plus B and C plus D. So because of that, the contents are A plus B is present in R1 and the contents of C plus D is present in R2, so that the mul R1, R2 and X is another variable, it represents some location. So mul R1 and R2 and X. Here the source operands are R1 and R2 and the destination operand is the X, and the contents of R1 and R2 are added and stored in the destination operand, that is X. Here we discuss about how we can execute the same example by using to address instruction. So already we discussed what is the to address instruction. So in the instruction we have one source operand and one destination operand. So by using these to address instruction, these are the steps how we can perform the a plus b into c plus d. So here the first step is a is transferred to r1 and contents of b and r1 are added and stored in r1, and here move c comma r2 means the information present in c is transferred to c r2, and the next statement is the next instruction is add d comma r2 means the contents present in d and r2 are added and the result is stored in r2. And now the multiplication is performed between r1 and r2 and the result is stored in r1. So the multiplication is performed between r1 and r2, and the next one is the result is again stored into x. So that is the execution of our example by using to address instructions. And here we have some representations and some notations are there how we can represent our instructions, and the first one is register transfer notation. So identify a location by symbolic name standing for its hardware binary address. So we have some addresses is there, so that address is represented by some symbolic name. So for example, location LOC is our symbolic name and R0 is our representation of register, general purpose register, and the contents of location are denoted by placing the square brackets around the name of the location. So for example, so LOC in the braces we can represent, so means the what is the meaning of this one is R1, the location arrow marks indicating to R1. Here the information present in location is transferred to register, and the next one is suppose R1 and R2 are added and these are stored in R3, means the R1 contents R2 contents are added and the result is stored in R3. So this is nothing but register transfer notation. And another notation is assembly language notation, represent machine instructions and programs. And here we use some mnemonics like move, add. So these are the some mnemonics, and these are the mnemonics used in our assembly language programs. And here it is same in the previous case we can discuss the location, the information present in location is transferred to R1. Here we indicating that arrow mark, but here irrespective of that, here we use some instruction. So assembly language notation, that is move LOC comma R0. So always the instruction, the first operand is source operand and the second operand is destination operand. What is the source operand here? LOC is the source operand and R1 is the destination operand. So and now we can discuss about instruction execution and straight line sequencing. And this is the one program. So this is the 3 instruction program. In that 3 instruction program, here we have move A comma R0, add B comma R0 and move R0 comma C. Here we have one example, one program, that is C is equals to A plus B. So the contents of A plus B are added and the result is stored in C. So this is our example. So how we can execute these instructions? First of all, the program is stored in our memory. So here we have different memory locations are there, I plus 4, I plus 8. How we can say that I and I plus 4? Because here word length is 32-bit. So whenever we have the 32-bit word length is there, the address locations are 0, 4, 8 like that. So here we consider the each instruction is 4 bytes long, so means the word length is 32 bits, so that the addresses are represented here. The first instruction is I and the next instruction is I plus 4 and the next instruction is I plus 8. So the program counter pointing to the first instruction, that is I, and that instruction is executed and the program counter is incremented by 4 and the next instruction to be executed and the program counter is again incremented by 4 and the third instruction is going to be executed. So this is the process how we can execute our instruction in straight line. So means the here we have three instructions are there. These three instructions are fetched by the processor and execute one by one. Here the word length is 32 bits, so that here address locations are 4. And the same straight line program is there. Here we are going to perform addition of n numbers. How we are going to perform addition of n numbers? So now consider number 1 and r0. The number 1 is transferred to r0, and add number 2 comma r0, and add number 3 comma r0. So like that we are going to perform addition of n numbers by using number of add instructions. And finally the result is stored in some memory location. Here the address locations are considered as I plus 4, I plus 8, and so on, I plus 4n minus 4, I plus 4n. And already we can say that the memory is used for to store the programs and also the data. Here we have some memory locations, some NUM1 means number 1, number 2. So these are the memory location to store the data. So and in the top of the memory we can store our instructions means program. So this is a straight line program how we can perform addition operation of n numbers. And here the same program is executed by using branching. Here irrespective of using number of add in the previous case, here we use only one add instruction to perform addition of n numbers. Here we use our branching conditions are used. Here program looping is used. What is a loop here? Here observe here, move n comma r1. So what is n here? N is one memory location. This memory location consists of number of entries to be added. So this information is transferred to r1, and here we use one register r0, and that r0 is cleared, and here we can start our loop operation. So determine address of the next number and add to the next number to r0. So we don't know what is the next number address, so in the loop we can find out what is the address of the next number, and we can add the next number to our r0. So the loop will be continuing. And here the decrement r1, here r1 is used as a counter. Why? Because every time the r1 register is going to be decremented. So whenever the decrementing is after performing the decrement operation, the result is greater than 0, the loop will be continuous. Whenever the result is not greater than 0, the final result is stored in sum. So this is the how we can perform addition of n numbers by using branching. Means the program counter here, in this case the program counter here, every time the branching instruction loads a new address value into the program counter, and that program counter consists of the new address. So the processor must be fetches that new address and executing. So here by what is the use of branch instruction means, here we have to store the next address instruction into the program counter. And what is the difference between straight line sequencing and branching means, in straight line sequencing generally the program counter always have the address of the next instruction, but in this case the normal program counter it is not having the next instruction address, but here the branch instruction always loads the new address into the program counter. Whenever the branching condition is not satisfied, means the branch greater than 0, it is not satisfied, the program counter is normally incremented. So that is the difference between sequence line programming and branching. Now we discuss about addressing modes. So what is the use of addressing modes means? So in the previous we discussed about the data is stored in our memory and how the operands are stored in our memory. So means the different ways in which the location of operand is specified in an instruction are referred to as addressing modes. So means there are different ways are there to accessing the operands or storing the operands in a memory is nothing but addressing modes. So there are different types of addressing modes are there. So we have different types of the addressing modes are there: immediate addressing mode, register addressing mode, absolute addressing mode or direct addressing mode, and indirect addressing mode, index and base with index addressing mode, base with index and offset addressing mode, relative addressing mode, and auto increment and auto decrement addressing mode. So these are the different types of addressing modes. So immediate addressing modes. What is the immediate addressing mode means? So in the instruction we have the operand. So means, for example, hash value. So what is the meaning of hash value? Means hash 5. So in the instruction we have the operand is present, that is called immediate addressing mode. And here register addressing mode. So in the instruction we can say that the name of the register. So means the effective address is the name of the register. Means, what is the meaning of effective address? Means where the operand is present, that address is called effective address. So here where the operand is present in the register, so that effective address is equals to RI. And the next addressing mode is direct addressing mode. Here in the instruction we can represent the name of the location. Here, for example, LOC is the name of the memory location. So whenever we can access the information present in our location, we can write the name of the location in the instruction. And where we have the operand, in the name of the memory location, so that effective address is equals to location. So where we have the operand, in the memory location LOC, so that here effective address is represented as LOC. So this is the direct addressing mode. And coming to the indirect addressing mode, and here indirect register addressing mode, indirect absolute addressing mode. Here RI. So in the RI means, here we can represent RI in braces. So in the instruction we can represent RI is in braces. What is the meaning of RI is in braces? Means here in the previous direct addressing mode, the effective address is itself, the operand is present in the register itself. But in this case the operand is not present in the register. In the register we have some memory address or the value. So in that particular location we have the operand, so that the effective address is equals to braces of RI. So means in the register we have some information, in that information we have the operand, so that the effective address is equals to braces of RI and effective address is equal to braces of location. So this is about indirect addressing mode. And now what is the difference between direct addressing mode and indirect addressing mode? In the direct addressing mode we can directly mention the name of the memory location or name of the register. But in this case we cannot having the information is directly in the register, it is present in indirectly. So that is the direct and indirect addressing mode. And coming to the index addressing mode, how we can represent index addressing mode symbolically? Means X of RI. What is RI? Means it is a general purpose register, and X is some numerical value. It is a constant, it is represent some numerical value. So here what is the effective address? Means the contents of where we have the operands. For example, RI is the 1000 memory location, and where we have the information, it is a not 1000 plus some X value. Suppose the X value is 2. So where we have the operand in 1002 memory location, means effective address is equals to the contents present in RI plus X value. The effective address is generated by adding the contents of constant value to the contents of processor register. So that is the index addressing mode. And next one is base with index addressing mode. Here how we can represent base with index addressing mode? Here we use two registers. One is index addressing mode, second one always considered as base addressing mode. How we can get the effective address? Means what is the effective address? The effective address is nothing but where the operand is present. So which memory location we have the operand, it is called as effective address. And in this addressing mode, how we can get effective address? By adding the contents of RI and RJ, means index register and base registers. So this is a base with index register, base with index addressing mode. And the next addressing mode is base with index and offset. Means here how we can represent base with index and offset? Here X of RI and RJ. Means how we can represent symbolically? Means X of RI and RJ. In the instruction we can represent X of RI and Rj. What is the effective address means? By adding the contents of Ri, Rj and also the value, means the constant value or offset value. So this is about index addressing modes. Here we have three types of index addressing modes: index, base with index, and base with index and offset. And what is the relative addressing mode? The next one is relative addressing mode. So what is the relative addressing mode is, here it is represented as x of pc. And what is x of pc means, here in the, it is same as the index addressing mode, only the difference is the processor register is replaced by program counter. So what is the effective address means, the effective address is generated by adding the contents of program counter to the offset value. So this is about relative addressing mode. Mainly the relative addressing is used for to finding the branching target locations in our branching instructions. So next one is auto increment and auto decrement. So these are the some additional instructions. And here how we can represent auto increment means Ri in braces, and after that we can indicate some plus symbol. So what is the effective address means? The effective address is the contents of processor register, and after accessing the operands, the contents of registers are incremented. And now what is the auto decrement mode? Here auto decrement mode is represented minus of Ri. And what is the decrement mode is, the first the contents of register is decremented, and then the decremented operands are nothing but effective address. So these are the different addressing modes used to accessing the operands present in our memory location. So now we are going to discussing about basic input and output operations. So what is the input operation and output operation for our computer? Already we discussed in the functional units what is the use of input and output. So the input is used for to provide the information to the computer, and output is used for to display the information outside the world. Here the input and output operations are very essential, and the way they are performed can have significant effect on the performance of a computer. Now we discuss about program controlled I/O example. So read in character input from keyboard and produce character output on a display screen. Rate of data transfer. Rate of data transfer from keyboard to a processor, and rate of output transfer from display unit processor to display unit is different. So because of difference in speed of operations, it requires a mechanism, that is synchronization of data transfer. How we can achieve the synchronization means by using some buffer register. So observe here, this is a diagram for how the input and output and processors are connected by using bus. And here input and output devices are having buffer register, that is data in and data out registers are there. So what is the use of data in and data out? So whenever the keyboard is ready to give the information to the processor, that information, so whenever the keyword is pressed by the user, that is stored in our data in register. So means in this, at this condition the SIN is equals to 1, means the status flag indicating that whether the buffer register is filled by the information or not. And the same as in the display unit also. So by using SOUT status flag, whenever SOUT is equals to 1, the processor, the display unit, it is ready to display the information, means the processor store the information into data out. So this is the use of data in and data out registers, and by using status flag we can say that we can determine the status of the buffer registers. And now we can, by using mission instruction, we can perform read and write operations. And here mission instruction that can check the status of the status flag and transfer the data. So here we have the read wait branch to read wait, and if SIN is equals to 0, otherwise input is transferred from data in register to R1. Here the data in is the processor register, data in is the input register, input buffer register, and R1 is the processor register. So by using this instruction branch to read wait, so whenever SIN is equals to 0, so there is no information in the buffer register, so we have to wait. And otherwise, so whenever SIN is equals to 1, So we can transfer the data into R1 register. So this is the read operation. And coming to the write operation, write wait branch to write wait if S out is equals to 0. So whenever S out is equals to 0, the display unit is not ready to display the information, so that we have to wait some time. So otherwise the output is output from R1 to data out. The information is transferring from R1 to data out register. So this is the how we can perform read and write operations by using mission instruction.